So I decided not to give any references. I mean, not to put, not to crumble the slides with references, and I just produced some notes for this course with all the references, in case you're interested or you want to. And they're posted here: tinyurl.com epit dash XML. So if you want to download, and there are also these slides. Which are so what I'm going to talk about is semi-structured data, logic, and automata. And by that, I don't mean like I will cover the union of the three, but I will focus on the intersection. So we're really going to work on what are the connections between semi-structured data, logic, and automata. So to start with, what is semi-structured data? I'm not so sure, but basically it's data which is structured but not necessarily in tables. So you have seen some, I mean, I wasn't here yesterday, but I've seen these slides. So yeah, there was some explanation by Pierre yesterday. So basically it is structured in some hierarchical way. Yes?
Could you write the URL on the blackboard?
Yes, good idea. Perhaps here. So it's stored in some hierarchical way. So we will consider that a tree. And it has some attributes and tags which allows it to define the semantics of the data without being too constrained by like in when we do in tables, in relational databases. So it has a self-describing nature. So there are many formats that are usually represented by this semi-structured data. We are going just to focus on XML, but other formats like JSON and stuff, they're basically the same idea. So why XML? Well, it is probably the most used format in the web. I mean, in fact, these slides are XML. They are made in HTML, which is XML. It is a very flexible and simple format for exchange and storage, and they look like a tree, and this is what we're going to be interested today. So in the relations with methods for formal methods for tree. So and what is an XML? Well, you all know what's an XML. It's something of this form. So you have opening tags and closing tags from some. We're going to consider that there are some finite, some well-defined set of tags, and there is some way of nesting tags one within the other. And there are also some other things like this, for example, which are attributes. I don't know if you managed to see anything. No, okay. So I mean, there are some things like attributes. I don't know if you managed. Like, let me do some. There are some attributes like name, for example, or ID, which contain some data, and also inside these tags, one could add data. I mean, the strings, let's say, when I say data. So this hierarchical format. We're going to describe it as a tree, as you can imagine. So yes.
So the attributes are not from a fixed set. It's only the tags who are from a fixed set, or?
Of course, that depends on the way you are modeling, but the names of the attributes, like
yeah, the names are from a fixed set.
so this is a tag, and this is an attribute name, and this is an attribute value.
Okay.
So names of attributes and tags, we will consider them from a finite set, well-defined set.
Okay.
Does that answer your question?
Yeah.
So basically, this XML, we're going to see it as a tree. As a tree, well, there are many ways of seeing it as a tree. This is the way I decided for this presentation. So we have tags and attribute names are internal nodes, and leaves contain the strings inside. No? So we have school, which had an attribute name with the string EPIT, and there was also some courses, and this is how we're going to represent it. So the usual tasks for XML is, of course, querying it, extracting information through. There are many languages. Perhaps the most popular one are XQuery and XPath, and we're going to see how they work, how the basic mechanism for querying with these languages, but also expressing constraints. So we want to be able to define what are the valid documents for our domain of application, and there are several schema languages like DTD, XML schema, relaxng. We're not going to I'm not going to define all these languages, but I will tell you later some connections. And of course, we can also we also want to do some reasoning on this on XML. So reasoning means like in static analysis, like working with a query or with a query and schema, and deducing something. For example, for query optimization, or to ask for the equivalence of two queries, or things like that. So. But in order to do this, all these things in a nice and principled way, for this talk, we're going to work with an abstraction of XML, in which we only going to work with on a finite alphabet, that is on trees with a finite alphabet. That is, we're going to forget about the strings part of the XML, and we're going only to work with the structure and the tag names. So basically, here we're going to forget about these leaf nodes and work on this basic structure of the tree, which is what we're going to do. At the end of the talk, I will tell you something what happens if we add these data values. Okay. Any questions? No? Okay. So and now why logic and automata on trees? Well, as I told you, since an XML is a tree, it's logical to try to formalize it by means of automata. So automata is a basic model of computation, and this is the basic way of trying to understand how algorithms work on trees. And besides, logic and automata are the foundation of query languages for design, for finding what are the expressive traits that we want to add to a language, what adds expressive power, what does not. And it also provides us with a fundamental toolkit, for algorithms and complexity bounds. And it's also allows us to study the expressive powers of query languages. So I will start defining what is I'm assuming that that you don't know what is a tree. So I will define everything from scratch. What is a tree automata? So first, there are several kinds of tree automata, of trees and of tree automata. So, for example, for automata, there's the possibility of how to proceed, how to navigate the tree, either to walk the tree, that is going from one place to the other one. I mean, just following the edges of the tree, or you can also work in parallel, bottom up or top down, by in some sense treating all nodes of the same depth at the same time, something like that. It could also be deterministic or non-deterministic, as in the word automata case, and it can be seen just as means for defining a language, or as a querying device, like answers nodes of a given tree. And on the other hand, trees can also be, it is often sometimes considered to consider unordered trees. In an unordered tree is a tree where we don't distinguish between the order of sibling subtrees. So, for example, these two trees in which this subtree and this subtree are interchanged, and also these two leaves are considered to be equivalent. And an ordered tree is one in which the order is important of the siblings. And also it can be ranked trees or unranked trees. Ranked trees is when there is a bound on the number of children that has each node, and unranked where there is unconstrained. So, of course, there is not, I mean, it's not a ranked, any tree is of course ranked, but I mean classes. A class of trees is ranked if there is a bound on the number of children for every node of every tree in the class, okay? Yeah?
So for XML, it would be unranked trees, probably, right?
In general, yes, XML.
And is it normally considered ordered or unordered, or does it depend on your use case?
Well, of course, in the format, in the way they are written, they are already ordered because there's a string. But it will depend on the formalism that you use. For example, if you use some, we will see XPath, for example, some sort of form, temporal logic in which you can only use descendant and ancestor, for example, we will consider them to be unordered. But of course, if you have the sibling ordering between the children of any node, then it will be ordered. But yeah, if you take from an XML file, you can extract an ordered tree in general. Yeah. Yeah.
Trees are finite or could be?
Yes, good question. No, finite. Everything is finite here. Of course, it doesn't mean that it doesn't make any sense to consider infinite trees, but in here databases, we will consider everything finite. So there are two possibilities, ranked or unranked, as Stefan was asking. So there are two models of tree automata, one for ranked classes of trees and the other one for unranked. So I will go briefly through both of them. So starting with ranked automata. So I'm not going to define very formally everything here. So I expect you to interrupt me with something which is not clear, okay? I will define by means of examples. So ranked tree automata is, as everything in computer science, a tuple. It has a finite alphabet, finite set of states, and some set of distinguished states. You can call it final or initial, depending how you're going to look at the computation. And then there is some finite set of transitions from this set. Like it has a word of states, a letter, and a state. And the idea is that each transition should be looked in this way. So if you have this transition in your transition state set, it's you should think of it as something like this: that if the children have states Q1, Qn, and the parent has label A, then the parent can have a state Q0. So this is the way. And of course, there is a special case in which this word, Q1, Qn, actually is the empty word. And this should be seen as something like this, that to a leaf node, we can assign the state Q0. This is how we're going to. So an accepting run is simply very close. I mean, for those who know what is a word automaton, it's like very close to how we define it for word automaton. So it's a mapping from nodes to states, so that the root node gets assigned something from this distinguished set, and the assignment is compatible with the transition. And of course, I'm not defining what compatible is, but I'm just giving you an example. Hope it will be enough. So consider this tree automaton. So it works on a finite alphabet AB. It has states E and O. E stands for even and O for odd. The final state is odd, and there are these transitions. I'm not sure you will be able to see, so let me just. It says if we have odd, odd, and an A here, then it gets even. If we have odd, even, and an A here, it gets odd. If even, odd, and A here, it gets odd. Even, even, and A even. Odd, odd, and B odd. Odd, even, and B even, etc. And the leaves get, if there is an A, we get even. If we have a B, we get odd. So can you imagine what this is trying to compute, or what is the language of this automaton? Exactly. The number of B is odd. Okay? So if we basically know that from this subtree there is an odd number of B's, and from this subtree there is an even number of B's, and we have a B at the root, then in this whole subtree there will be an even number of B's, and so on. So this is what is trying to compute. And what I mean by that the mapping has to be compatible, it means that every node with his children in the tree has to find its corresponding transition here. So for example, in this tree, which is accepted by the automaton, it is accepted because these three nodes can find the transition here. So there is an A with odd and two children O and E. So we find this here. The same one here. We find another one here. This one here. And for the leaves as well, we find for each one of them. So this means just to be compatible.
In your definition of this tree automata, where is ranking?
So the fact that all these rules, these transitions, have all of them, as you see, have either 2 or 0 children.
But this is not part of your definition.
It is implicit in the definition, in the sense that since there is only a finite number of transitions, there is a maximum number of children that they will have, right? The transition. In this case, it's 2. So this automaton can only accept trees which have at most 2 children. So I could have put also like k as part of the definition and say, well, transitions can only have at most k children. But since it's a finite subset, I could take, for example, this plus one which has 500 children, but still will be ranked, right? Yeah.
And in this model, you assume that your tree is ordered, or
Yes.
or your transition function is symmetric, I guess. Or
Of course, yeah. In full generality, it is ordered. Of course, if you would want it to be made unordered, then you would require that the transition function is symmetric. That every time you have something here, you have the opposite on the children. I mean, any permutation. In this case, since there are two, it's only just symmetrism.
and those are models that have different names then, or
I don't know about. Perhaps someone in the audience knows, but I don't know of any name for that restrictions.
okay, it's just because I always get confused about these things.
Yeah, but me too. So I don't know. So, as you see, I mean, is an except, sorry. So is this computation bottom up or top down? It is neither, right? Or you can think of it, if you want, as if one could think of we start with the final state at the root, and then we proceed downwards until we find states as the leaves that come from here. Or you can think of it as bottom up. We start with leaves which get assigned states from this set, and then we proceed upward until we arrive to the root with state from the final state. So here in this model there is no notion of bottom up and top down. In some restrictions we will see later for determinism there will be a difference, but this is just it's the same. One can think of bottom up or top down, or simply just, as I define it, an assignment compatible with that maps the root to this set. Okay, this clear? This has to be clear, otherwise we will be in trouble later. Okay, so on this, for thinking about these trees, is something useful is to define what is a context. So a context will allow us to do concatenation. It's like a string concatenation on words. It will allow us to do something of the sort. So a context is just a tree with some distinguished leaf, and basically this context allows us to apply the context to a tree or to another context, which is the result of replacing this special leaf with the tree. It will become clear here. So this is a context, for example. It is a tree and it has some special leaf. So we can apply the context to a tree and we obtain this. So basically we stick the tree here. Or we can apply the context to another context, for example to itself, and we obtain this one. Okay? So this is just a context, is just that, a tree with a hole. And this allows us to define a pumping lemma for trees. The pumping lemma says as follows. Let me put it bigger. So it says for every I'm not sure if I define regular tree language. For any language accepted by a non-deterministic tree automaton, as we have just seen, that henceforward I will just call regular tree language, which is the usual name. For any regular tree language, there is some k, some number, so that every tree which has at least height k, there is another tree and some context, so that T can be decomposed in these ways. The first context applied to the second context to this tree. And for every iteration of the context, of the middle context, this is in the language. Okay? So if you know what the pumping lemma is for words, you could replace C1, C2, and T prime by words, and you get the pumping lemma on words. here, of course, the concatenation of trees, they need this definition of context, and we get something like this. So what does it mean? It means that basically this K of the pumping lemma is, you have to think about the number of states of an accepting, of a non-deterministic tree automaton recognizing the language. So if there is some sufficiently long tree in the language, then there must be an accepting run, as we define it, where along some branch, this because it must have some very long branch, along this branch there must be some state that repeats, for example, state Q. And then we simply define this tree hanging from here as T prime, this other one as context 2, and the first one as context 1. And it says basically that since the state is the same, we could, for example, remove completely the second context, and we arrive to something like this, which will still be in the language because this is still an accepting run. But we could also iterate it because it's the same state. We can put the context twice, for example, or the context 3 times, or any number of times, and it will still be in the language. Okay? And another classical characterization is the Myhill-Nerode characterization for 3 languages, and which is characterized in terms of this congruence relation, which is defined as follow for any tree language L. So here it's not a regular tree language, any tree language, any set of trees. Okay. We define this equivalence relation, which says that T is L equivalence to T prime if for every context the context applied to T is in L, if and only if the context applied to T prime is in L. So its membership in L is invariant under applying any context. Okay. And we get this result, which is basically the same result as for words. So this lifts up. Yeah.
Isn't it rather the syntactic congruence?
Syntactic congruence.
Rather than the Myhill-Nerode equivalence.
Ah, how it's called? You mean the?
If you do Myhill-Nerode, you just take U minus 1L. You just have context on one side.
Ah, okay. This is the syntactic congruence.
This one's, I think it looks like
here you see
syntactic
exactly because you have right and left.
Because you have
Ah, because you don't have right and left. You have only.
for
you have only right.
It's one-sided.
Mm-hmm.
For the syntactic congruence, it's two-sided. So I don't know. It looks to be two-sided.
Because why two-sided? Because here you have only one side.
Because you can have the hole in the middle.
It would be two-sided for context, no? For context, you can plug in a tree and
Before and after, yeah. Yeah. So this is the syntactic congruence.
Mm-hmm.
Okay. But I because this is just plugging it on one side, right? You're only applying it at the bottom of the tree. Or at the top of the context, if you want.
Depends how you represent words. It's just like that, and you have hole in the middle.
Yeah, that's my point.
Perhaps not to lose too much time, we can discuss that on the coffee break. But the important thing is that we have this nice characterization with this congruence relation. We can call it as we prefer. That the language is regular. Remember, regular means recognizable by this non-deterministic tree automaton. If and only if this congruence has finite index. Finite index means has finitely many equivalence classes. Okay. And besides being a nice characterization, it also gives the fundamental results to define the minimal automaton. So basically, the minimal automaton is an automaton which has the smallest number of states, and it is just defined by taking one state per equivalence class and defining the transition relation accordingly So I'm not going to give the details now, but later. So let me now tell you what about determinism. So is there a deterministic version of this tree automata? So as I had told you, for non-deterministic tree automata, one can see the computation of top-down or bottom-up. It's basically the same. It's the same definition. But for determinism, it will not be equivalent to define it top-down and bottom-up. At least it yields two different definitions, and we will see that these two definitions are actually not the same. So let me define both of them. So there is deterministic bottom-up and deterministic top-down. Deterministic bottom-up, it means that for every sequence of states, Q1 to Qn, and for every letter A, there can only be at most one state, so that this transition is in the transition set. Okay, so it means that once you know what is the state of each one of the children, and once you know what is the letter of the parent, there should be either there is no transition and then the computation stops, or there is exactly one. Okay? Is this clear? And in fact, the good news is that non-deterministic tree automaton can be determinized. So what does it mean? That it means that from a non-deterministic tree automaton, one can construct a deterministic tree automata, a bottom-up deterministic tree automata, as we just saw, which recognizes the same language, exactly the same language. That's the good news. The bad news is that it takes exponential time, which is unsurprising because already for words it takes exponential time. And this is very similar to what it's done in the word case, is through the so-called power set construction, which is extremely simple. Given a non-deterministic tree automata, one can define a deterministic tree automata by taking, instead of the states, the power set of the states. So we have all subsets of the states. Instead of the final states, we take all those states which have at least one final state. And instead of the transition relation, we define a new transition relation which goes as follows, and I think you can't be able to see. Which goes as follows. It says put in the new transition relation all transitions from that read letter A and capital S0 and capital S1 to Sn. Remember that these are sets. So that S0 are all those states that can be reached from some state in S1 to Sn. Basically, there is, so that there is S1, small S1, small Sn in S1, Sn, respectively, so that this transition was in the original one. Okay. So basically, we keep track in parallel of all the possible computations from those sets. Okay, is it clear? Okay. So it follows that this one, of course, given states S1 to Sn and A, there is exactly one S0, right? So it is deterministic. And one can see that it recognizes the same language, actually. Okay. Yes, of course.
From how you define it, it's no longer finite, right? But I guess if it's empty, then you just don't put it or something. I mean, this set delta prime is not a finite set.
It's not a finite set. I see. You're right.
Why not?
But I think it is because you only put those here so that there exists. No, you're right. Sorry.
Why is it not finite?
If you take a very long string of sets,
Yes. You can have arbitrarily many sets here with empty at the top, right?
But we're ranked, aren't we?
Yes, but the way I've defined the tree automata, I skipped the fact that how ranked they are. But yeah, this should be
if non-empty.
if non-empty.
Yeah.
Yes, S1 is equal to this, and S0 is equal to this, and S0 non-empty. Yeah, thank you. That's a good remark. Okay. So what about deterministic top-down? So for deterministic top-down, remember that before we said if we know the states from the children and we know the parent letter, then there is at most one state in the transition. Here we can do the same, but in the other way. So if we know the state of the parent and the letter of the parent, then there exists at most one transition that tells you how to label the children with states. So, for example, in the example we had seen, there were many transitions, but among them there were these two, which says if we have an odd and even and a B, then it's even. If we have even and odd and a B, it's even, right? So this is not deterministic top-down. This tells us that the automaton we had defined is not deterministic top-down because there are two transitions that share the same information on the parent, but have different information for the children, right? So one question would be, can this be made deterministic in general or in particular for our example? And the thing is that no, it cannot be made deterministic. Actually, deterministic top-down tree automata are less expressive. This is these equalities and subsets are in terms of expressive power. So deterministic top-down tree automata are less expressive than deterministic bottom-up tree automata. One example is just exactly the language we had seen. This cannot be accepted. And in general, deterministic top-down tree automata, they are very weak in expressive power. It's not that just this is some special language. They cannot accept many things. They can only basically make tests on the path, basically every path of the tree verifies some regular property, something like that. And as we had seen, deterministic bottom-up, on the other hand, it is the same in expressive power as non-deterministic tree automata. And we can even add some, like the possibility to travel the tree in a two-way fashion, which I'm not going to define. Yeah.
Is there a notion of deterministic unordered trees or unordered automata? Something that would just look at the multiset. Well, say that if you know the root, the state of the root and the labels, then you know the multiset of children, but not the exact word, because that would recognize the odd number of bees. I don't know if that would be.
No, I don't know of any definition in that sense, but yes, for that particular language, I think you're right. It could. Well, but I don't know. I mean, for that rule,
I know there is another rule.
There is another rule that will break. But for this one in particular, you're right. Yeah. But no, I'm not aware of any definition of deterministic unordered tree automata. Other than, I mean, one could make up a definition saying you just remove all things which are symmetric, and then you test for determinism. But
is there any study about
Yeah.
it, or any properties that are interesting?
I don't know. No. I'm not aware of. Sorry. The other. So deterministic bottom-up is the same as non-deterministic tree automata, and this is also the same as adding alternation, adding two-wayness, which I'm not going to define because it will take me too much time, but this tells us that it's a very robust class, and it mimics in some way what happens on words. And this is why it's called regular tree languages. So it's invariant under having alternation, two-wayness, deterministic, have the same expressive power as non-deterministic. Okay, what's next? Okay, so now we can see some closure properties, basic closure properties of tree automata, and some decision problems. So with regard to closure properties, so there are some which are very simple. So for example, intersection, the fact that it's closed in intersection, it is done also similarly as for words. It is closed in an intersection, first of all. It is in polynomial time. And one can construct what we usually call the cross-product automaton. So we have two non-deterministic tree automata. We can construct the automaton that recognizes the intersection as follows. So for every time we have some transition in the first automaton and some other one in the second one, we just of the same arity with the same number of children, then we construct in the cross-product automaton the one that goes that uses pairs of states. I mean, states from one on the left and the other one on the right, which mimic the same thing. So if we have Q1, Q2, Q0, P1, P2, P0, and the same letters, the same letter A here. I don't know why I put here, so this should be empty. Q1, Q2, Q0, A, and P1, P2, P0A. Then we produce Q1, P1, Q2, P2, and Q0, P0A. Okay, and this is this recognizes the intersection, okay, of the languages. Union, it's even simpler. So if we want to produce the union of two non-deterministic tree automata, we just take the union, the disjoint union of the states, the union of the final states, and the union of the transitions. So then it will be, I mean, of course, making sure that it's disjoint. We're sure that a tree is recognized by this if it's recognized by either of the two, A1 or A2. Okay? Complement, well, this is the most interesting one. This one is also in polynomial time, even linear. And complement is the most costly one. It's in exponential time. And for this, yes?
The complement is with respect to which big set?
Yeah, this we have to be given the K, the arity, yes. Or we can take just the maximum number of, yeah.
And the alphabet in general is going to be fixed because you put it as part of the automaton.
For the complement, yes, of course. For the complement, you have to fix the. For intersection, well, you can just take the I mean, it's the same. It doesn't change anything. But for complement, yeah. For complement, we have to first fix what is the universe of trees that we're complementing. So we have to fix the alphabet and the rank, the maximum number of children. And to complement, we will first need to determinize the automaton, that's to do this power set construction we had just seen. Then we can complete the automaton. Complete, it means that there is no way that we reach a deadlock, that we can always continue the computation in the tree. There is no way that we will reach some number of states, some configuration of the children, so that there is no transition that allows us to label the parent with a state. So more formally is like how we can do this. We can add just some new states, some dummy state, Q bottom, make sure that this Q bottom is non-final, and then add everything from here, like everything from this K, this is what Emilia was asking, this is something fixed. So every possible transition so that it wasn't yet defined in the transition relation, right? I mean, every possible every transition for every word of states and label for the parent, so that it didn't find a transition in the set, we add this something that goes to this Q bottom. Okay, this is how we complete it. The important thing is that it's still deterministic after we complete it. Okay, this is why. Otherwise, we could just add this, of course, but I'm adding only those which didn't have already follow up in the computation. So, okay, is this clear? Or? So this we completed. Of course, if here, the important thing is that K is fixed. So this thing is polynomial. So adding this is a polynomial operation. So we have to add a lot of things, but if K is a fixed value, then this is polynomial. And then we simply switch final and non-final states. So we replace F with Q minus F. And this recognizes the complement. So if the input automaton was already deterministic, of course, we don't need to determinize it because it's already deterministic. And as I just said, this operation is polynomial, and this one as well. So it is in polynomial time.
Can you prove that there is not a better algorithm? I mean, is it mandatory that you start by determinizing the automaton for recognizing the complement?
That you need to determinize it necessarily? No, I don't think there is a result showing that. But I don't know, generic. I mean, something that you are forced to determinize it. I don't think you can.
No, but you may have nevertheless.
Examples at the beginning,
Yeah,
that is obtained by determinization.
Yeah, but okay. I mean, there could be another method which doesn't go through determinizing.
Still state lower.
Yeah, no. Okay, yeah. If that's the question was if you necessarily obtain a larger, an exponentially larger automata. Sometimes, yes. Sometimes there is no other way. You will obtain an exponentially larger automata. Yes, there are examples, languages classes of languages for this. Yeah, but of course. In principle, there could be other ways of complementing, which doesn't go through determinization, but this is very difficult to prove, of course. So, decision problems. Now, in my defense, at the beginning, I wanted to make it look like an ancient role, but then I started putting these dots here to separate things, and then there was no other choice. So decision problems. So the first one is the most important one, perhaps, is membership. Whether given a non-deterministic tree automaton and a tree, if the tree belongs to the language of the recognized by the automaton. So this is decidable in polynomial time, and actually it's slightly better than that. It is in a class which is slightly better. It's more parallelizable, let's say, which says basically, which is it's log space interreducible to context-free grammars. But for those of you which this doesn't mean anything, don't worry. It's in polynomial time. Okay, and
this is combined complexity, right?
This is combined complexity. Yes. And if the input automaton is deterministic, it is slightly better. So it's in the respective deterministic complexity class. And the emptiness problem is giving a non-deterministic tree automaton whether it accepts the empty language, which is also in polynomial time. And the idea is that we can just make the simplest saturation algorithm, which will try to add all states. We obtain all states which are reachable. Let's say, for example, bottom up. So we start with all the leaves, with all the states for the leaves which are reachable, and then we continue like this. And at some point it stabilizes, since there are only after some linear number of iterations it stabilizes, and we obtain all the possible reachable states in the automaton. And if there is a final state inside, then the language is non-empty. Otherwise, it is empty. Yes.
C stands for complete.
Complete. Yes. For the hardness for the polynomial time, it comes from path systems, which is basically a problem which is known to be p-time complete, which is very close. It's like some sort of deduction problem with rules, which is basically almost the same as tree automaton. Yes.
It's also the same as context-free grammar emptiness, which is even a bit closer to how tree automata states.
Yes, it's true. Yeah. For the reduction, yes. Yeah, I don't know if you heard. So what Wim was saying, also for this reduction to context-free grammars is basically the way. I mean, if you see the transitions, and you instead of calling them states, you're calling the non-terminals of a context-free grammar. It is a context-free grammar. It's just sorry. So then the finiteness problem is whether a non-deterministic tree automaton recognizes some finite language or not. So for testing this, the idea is that we first find something which is often called useful states. Useful states are those states which appear in accepting runs. So there are trees for which this state is sometimes reached. So imagine that there could be some states which, for example, there could be, in the extreme case, there could be some states which do not appear in any transition. In that case, those are not useful. There could be other states that appear in some transitions, but they can never be reached by any accepting run. Well, there is a way, in polynomial time to find which are these useful states. And then we test whether there is a loop on these states. Basically, whether there is a path or a word, a sequence of states that starts in and starts and ends in the same state, and that follow the transition relation, which uses only useful states. So this is, I'm hand waving here. But this is, well, this is in polynomial time. This is actually in non-deterministic logarithmics space. So it is in polynomial time, everything.
Oh, so it's not complete for polynomial time.
It is not complete for polynomial time?
No, I mean, this is what you just said. You said it's a non-deterministic logarithmic space. So
No, the second one, yeah.
oh, the second one.
Yeah,
okay.
the first one, it is complete for polynomial, yeah.
Okay.
Yeah. So yeah, if we, that's a good remark. So if we start with an input automaton which we're sure that doesn't have non-useful states, then it would be in NL, yeah. And then the universality problem asks whether, again, we have to, fix some k and a. So k and a are fixed. Fixed means they're not part of the input; they are fixed beforehand. And given a non-deterministic tree automaton, the question is whether the language recognized by this tree automaton is the set of all k-ranked trees over the alphabet A. And this is in exponential time. So the algorithm is very simple. We just complement the automaton with the same k and a, and we test for emptiness. And as we saw, testing for emptiness is polynomial time, and complementing is exponential time, unless we start with a deterministic automaton. So actually, if the input automaton is deterministic, this is in p time, because complementing is in p time, and testing for emptiness as well. Okay? And then we have containment, whether the language of one automaton is contained in the other one. Again, we do this. We do complement, and we do intersection, and we test for emptiness. And this gives an exponential time procedure. And if the automaton is deterministic, this gives a polynomial time procedure. Okay. And then we have the equivalence problem. So whether the language is accepted by two automata are the same or not. And for this, we reduce to the containment problem. So we test for both containments. And then there is this problem, which is perhaps you won't find it too natural, but actually it's useful. I have used it at least. The emptiness of intersection, of k-fold intersection. So the emptiness of intersection of two automata, or three automata, or five automata is in polynomial time. But here the question is whether we're given some n and n automata, and we want to know if the intersection of these n automata are empty or not. But the number of automata that we receive as input we're free to choose. It's independent of the problem. So it is in exponential time. That's the easy part. So we construct the intersection, and this will give an exponential automaton, because this k is part of the input. So we will get an automaton with an exponential number of states, and we test for emptiness. Okay. The interesting thing to note is that it is also hard for exponential time, this problem. Okay. you have any questions here so far? Yes.
Just as a follow-up to the question over there,
Yes.
what is data complexity then? of these?
Well, what do you mean?
Where you fix the automaton.
So these are
For those, it doesn't make any sense, but for the evaluation.
only for the for the valuation. So for the valuation, it's linear. This one evaluation membership. So I will sometimes say membership, sometimes evaluation, sometimes model checking. Just it's the same. I'm just thinking about the same problem. So the membership, it's if we fix the automaton, so we don't take it as part of the input, it's linear in the tree, right? It's just evaluating, I don't know, in any way we want the tree automaton. So it's just producing all the possible states of the automaton that can be at each node, and we can do this in one pass of the tree.
You can probably parallelize that, no?
Parallelize that? Yes, in a natural way, like in the tree. Yeah.
Is it still complete for log CFL, or can you push it down to, I don't know, AC0 or NC1 maybe?
I don't know. Wim, do you know?
I would have to think about that.
So when I say if you have questions, only easy questions. Huh?
But you might have probably in NC1, right?
Yeah, I don't know.
But the combined complexity is already log CFL, so it is already highly parallelizable.
Yeah.
Yes, even in combined complexities. I mean, if we take log CFL as highly parallelizable, yes. And this was the last one. So emptiness of intersection, and then this one. This is not a decision problem, but this is the problem of given a non-deterministic tree automaton, produce a minimal automaton. That means an automaton with as few states as possible. Okay, and this is possible to do in exponential time, or if the input automaton is polynomial, then we can do it in polynomial time. The input automaton is deterministic, then we can do it in polynomial time. Sorry. So how do we do this? First, as we did before for complementation, we construct a deterministic tree, an equivalent deterministic tree automaton, which is complete in the sense we had seen before, and reduced in the sense that we remove every state which is non-useful. We already saw how to do this. And then we define an equivalence relation which somehow mimics the congruence relation we had seen for the Mayer-Nerode theorem, but on the states. So it will be an equivalence relation on pairs on states. Sorry, on the state space. So we start with the final state. So there are only two equivalence classes: the finals and non-finals. And then we iterate this relation by making it finer and finer and finer until it stabilizes. So what do we do at each step? So at step n+1, we will have all the pairs of step n. So that verifies something. Okay, so P and Q will be n+1 equivalent if they are n equivalent and now I see that perhaps it is not visible. Just put bigger. So that for every possible sequence of states and every pair of states of the, so for every two possible sequence of states of the children, and for every possible two states of the parent, and for every label. So basically, if we have this and that in the transitions, so from, surrounded by the same states, P and Q go to R1 and R2, then R1 and R2 must be necessarily n equivalents.
Do you have the same confinement as for strings? The complexity for strings is if n is the number of states, it's O of n log n. So do you...
If n is what is
states,
yes, but what is n log n?
It's constructing the minimal automaton.
If you, starting from a deterministic automaton? Ah. I don't know, frankly.
The complexity of this algorithm, is it quadratic or is it
I think it's quadratic. Yeah.
I think there is an extension to the technique that this partition refinement algorithm can also be extended to that.
Ah, okay. So it.
The naive thing is n squared.
Mm.
If you do your partition refinement using some fine data structure, I think you get n log n.
Ah, you get n log n.
Is it an intuition or is it something?
No, it's published. I've seen the paper.
Okay. So apparently it is. It can be done in n log n, but this gives a quadratic algorithm. So this is how we define at each step the equivalence relation, and as soon as we find some n so that the equivalence relation is the same as its predecessor, it stabilizes, then we stop, and we can already build the minimal automaton by replacing every state with a representative for its equivalence class, and that's it. And we replace it everywhere, like in the transitions as well. And this is the minimal automaton. Okay. And of course, if the input automaton is deterministic, then we don't need to construct the DTA, and both to complete and to reduce the deterministic tree automaton is polynomial, so everything becomes polynomial. Okay, so this is the ancient role. So what about unranked trees? Because actually in real life and the web, most trees are actually wider than taller, so they're fat and short basically. So we have to be able to deal in a principled way with unranked trees. How do we do this? We can also define an automata model for unranked trees. So what is the unranked tree automata? It's exactly the same definition. So the transitions come from here. But if you remember before, I had put like some subscript fin to say that only finite subsets. Now we can take infinite subsets. But we have to, of course, impose some further restrictions. It can be any infinite subset which is regular. Regular in the sense of regular for word languages. So what does it mean? So in some way we can define it, for example, as a set of triples of language a regular language from Q star, a letter A, and a state, and some finite set of triples of this form. So this is how we can represent a regular subset of this. Okay, so I'm not going to define what is a word automaton or regularity for automata, but we can just take it for, I mean, or as a one-ranked tree automata if you want, or as a black box if you prefer. So some representation for a regular set, subset of Q star, a letter, and a state. These are the kind of the finite set of these triples that we will have as transition.
Is it the case that every XML file is given by an unranked tree regular automata?
Every XML file, can you repeat, is given?
Is given by one unranked tree regular automata?
I'm not sure I understand your question. So, I mean, an XML file is like one tree.
Yes.
It would be one.
Yeah, because you want.
And this is like, yeah, to define classes, exactly, classes of trees.
I just wanted to understand if imposing regularity is actually a strong constraint or not.
Ah, I see. So for that you have to consider not a particular XML, but perhaps a family of useful XMLs that you find somewhere. But the thing is that in the web, to define families of XML, one usually used constrained languages for XML, which are specifically designed for what are the XML documents that I'm interested in. So there are different ones: DTDs, XML, schema, relax, ng, and it turns out that all of them, I mean, for these languages there are some things which talk about the data, actually the strings. But if we forget about that, and we only speak about the structure and the tags, it turns out that all of them, which are the most usual ones, can be expressed by this automata. Yeah. So again, an example. So this is basically the same example as before. So an odd number of B's, yes, an odd number of B's. But now we're not restricting to binary trees. We have any unranked. So we have the same as before, the alphabet, state space, and final state. But now the transition relations, this, instead of regular languages, I'm writing regular expressions which denote regular languages, which this one, I think it's too small for you to see, so let me just do this. So this one says if there are an even number of O's, so here it says E star, O, E star, O, E star, but we put a star on everything. So this says even number of O's, and I read an A, then it's even. Even number of O's and I read a B, then it's O. Even odd number of O's, so this is even plus some final O, and an A, then an O, and with a B, an O. Okay, so actually now it's kind of simpler to define it in some sense, because we can define with regular expressions what is even number of O's, and so for example, before we had to define specifically one transition for the leaves. Now the leaves are going to be automatically here, right? This is like iterating 0 times this sub-expression. So the epsilon, the empty word, is inside this regular language. So we're covered also for leaves.
just to make sure that I understood. So this language is arbitrary. I assume it is stable under commutation, because if it's unranked, this means you just consider two possibilities, no? So that means the language has to be closed under commutation, or no?
No, unranked doesn't mean unordered. Unranked, it means just that there is any number of... Okay, no worries. So on this tree, for example, well, I won't go through the accepting run because I think you already saw the idea. This is an accepting run, and the accepting run is defined as in the previous case. The only difference is that now we have to look at things at nodes with its children, and the children can be unboundedly many, but we have just to look at the word that is read by the children, for example, O, O, E, O, O, and an A, and we found here the transition that corresponds. Okay. Questions? Is this clear? Yes. Okay. I have no idea how much. I'm very bad at estimating, so I think it's fine. So what about deterministic unranked tree automata? As remember, for ranked tree automata, we had two versions of determinism. For unranked tree automata, we also have somehow several possibilities. So I will just mention two. Perhaps the most intuitive one, which is the first one that comes to one's mind, or at least to my mind, when one tries to define determinism for unranked tree automata, is this one, which I call possibility one, which to take basically the same definition as for deterministic bottom-up tree automata. So basically that there are no two distinct this is for deterministic tree automata. It says that there are no two distinct transitions in the transition set. So here I thought I had defined it, but okay, I didn't define it. Well, I think I forgot to write something. So what would be this translated to unranked tree automata? That there are no two. So here we had words before, now we have languages. There are no two transitions with language. No, sorry. Forget what I said. No, this is correct. So basically, this is exactly the same definition as for DTA. So there are no two triples which are in this transition set. So basically, if you know what is the states of the children, and you know the parent label, there is no way that you can find two distinct states in the transition set, which are both in the transition set, right? Okay.
You mean with the same language?
This implies that in particular you won't have two languages with a non-empty intersection leading to two different states by reading the same letter, but this is implied by this. Yes, this is what I mean. Okay, because I remember I defined, technically I defined this as a subset of this, which happens to be regular, and therefore can be represented in this way. But is this clear? Because perhaps yeah.
But then you say nothing about how you recognize the W, right? I mean, if you have a deterministic automaton to recognize
how you test
on the children,
how you test whether it is deterministic.
Yeah.
In this sense.
No. I mean, how you test if basically you have the word on the children,
Yeah,
right? And you say nothing about how you recognize that word.
exactly.
Okay, so that can still be non-deterministic.
Totally. Yeah, this is this. So it's just nothing on how we're representing
So
delta. So this is a condition on delta, but doesn't say what is the representation. It could be represented with a non-deterministic finite automaton, for example.
That would be weird, right? Because
That would be weird, of course. It's like, yeah, makes not much sense. But still, we can replace, we can add this determinism. We can make this finite automaton deterministic, for example. And yet, if we do that, we still bump into troubles. So even if everything is deterministic, like all automata, all languages that we're defining are deterministic in the word case, there is no unique minimal automaton. There are examples in which there is no unique minimal automaton, and still, for example, the universality and containment are not in polynomial time, as one would expect from a deterministic automaton.
But then you have to talk about the representation of your data, right? So
Of your data, of the delta, yeah.
Minimal.
Right.
if you want to solve these problems, then I'm pretty sure it will depend on the representation of data. How doesn't it?
Totally, yes. Yeah, so the thing is how to represent delta in such a way that it allows for a canonical minimal automaton, a unique canonical minimal automaton, which makes also universality, containment, and etc. Polynomial time.
Okay.
So there is a solution for this, which is called the possibility 2. Stepwise determinism. So the idea is that basically one has one defines delta as a bunch of automata called I think usually hedge automata, one for each letter of the alphabet, and these automata share the same state space as the original automata, the tree automata. They all share the same states. These are word automata that are deterministic, and basically they read everything works bottom up. So they start reading the siblings of the leaves, and the last state in which they end, it goes to the parent, and this goes on. So I have a small example here that I hope it will make things clear. So as I said, we have a word automaton for each letter, and everywhere in the tree, everywhere we find a letter A, we will apply to the states of their children the automaton corresponding to this letter A. And we're working bottom up. So we are assuming that we already have labeled the children with states Q1 to Qn. And we're going to run this deterministic word automaton. So it has some initial states, of course. It has some set of final states. And it will run. It can be that it doesn't accept the word. In that case, the computation finishes. If it accepts, then it accepts in a final state. And now how we continue the computation from here? Well, we just copy this state to the parent. Of course, for the special case of leaves, well, we will have what happens with the empty word with this automata, right? So this is how leaves are labeled. Is this clear? It's not a difficult concept. It's just that we use everything on the same state space, and you could think of this word automata as transducers which output exactly one letter, which happens to be a state from its state space, basically. And they are deterministic. So. Okay.
And then
So
you
this-
then I guess
yes.
you compute a new state depending on the letter and on the state that you got from your children or something like this, right? You still need one transition.
So can you repeat? Sorry.
No?
It's just a copy of the final state.
But how do you take into account the A then?
The A is because you apply this automaton, right?
Ah, okay.
There is one
You took
fine.
that into account before, actually.
Exactly.
Okay.
So one finite automaton for each letter of the alphabet,
Okay,
or of
okay.
yeah. Or
I'm getting it slowly.
yes.
Cannot we define this in the parity automaton way with a logic formula that has to hold on the successors and some is it kind of
But the thing is, I don't know, to test. I mean, you have to make it deterministic, like in some way that. I mean, it has to be a representation. I mean, the idea is to make a representation which is, which makes, for example, universality polynomial time. I don't know. I'm not exactly sure what you mean by using a logical formalism for the.
you